Okay, here it is again. It just came in minutes ago. Physicists use a single molecule as a tiny particle collider. They're still using molecules, atoms. We use light. Light is 1,000 times smaller than the particle that they're using. They want to see that little particle that we are started with. But to see it, they're starting with the big things. And then I understand a little bit about what they're trying to do is to see what's inside and glues the nucleus together. But I think I understand without seeing that. And it's just nothing more than magnetism attracted to a dark core. This is not what the dark nucleus, the nucleus of an atom looks like. It's not like that. The nucleus of an atom is like this. Boom. The dark matter goes to the center. It's always coated by white particles surrounding it. Unless you can smash them in a particle collider, and then you get all bits and pieces. Or you can do what we did, is take a couple of little bits and pieces and force them into a condition where they had to separate. And that's exactly what we did. Okay, just to refresh you on dipole electron flood theory. Everything there is made of black and white particles, or whitish particles, glowing particles, energetic particles. These are black or dark matter, literally dark matter. And the white, or the glowy part that attaches to it, the electron neutrino, attaching to the muon neutrino, which is dark matter, makes up a dipole electron. And when you take two dipole electrons together, that's all these are. When these attach together, that's a dipole. All right? Di means two poles, positive, negative. All right? The negative is extremely powerfully attracted to the muon, which is the dark matter. They can be separated, which I will show you we did separate them, but normally they're found together. At least in this, which is basically heat. A plus and a minus together, all by itself, is heat. It can migrate into something and warm it up, and it can back out if it's accepted somewhere else. This is what a photon is. It's two of these back to back. This is basically stable. This is basically on the margins of stability. This wants to be hooked up with somebody else that wants one of these. That's all that is. It's just an extra one riding along for the road. And it warms things up because it's sort of pushing in on another field. When it leaves, it gets cold. More electrons flowing in, or gluons, dipole electrons flowing in, warm things up. As they leave, they cool things down. Okay, my friends, every day now I'm getting more about them looking into photons using cell phones, exactly what we did here, and seeing the particles that they have seen in these huge collisions. Now they're still staying with the huge collisions, but they're using now the cell phones to see them, and they don't need the particle colliders anymore. I'll show you what they are doing, and this article just came in minutes ago. Hold on. All right, what they're doing is they're using a tiny little molecule. A molecule means it's a bunch of dipoles. Dipoles are the smallest thing there is. That's like a dipole electron. It has a positive and a negative, that's all. And you put 1,840 of them or so together, and they become stable, and you would call that a hydrogen nucleus or a proton, same thing. It's the smallest stable ball. The only other thing that's stable, smaller than that, is light. And that is stable with this right here. That's red. a red laser light. The green is identical, only it's green. Now this is red, and these are the same two particles they have found at CERN, and I've shown this many times, so I'm not going to get into it deep. We can accelerate it. Einstein was wrong about that. The particle wave duality is because there's a big field surrounding that particle, and as it comes through the air, it makes a big field, a wave. And the particle is because it's inside the wave, and we know that because you try to put two magnets together with the same polarity, they push each other apart. And you can feel the bang, 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 and it's just like going through the air. That's what makes the wave. So wave, particle, no problem. Dipole electrons, no problem. That is what I call atomic vapor. This is atomic vapor. That means that inside the atoms, they condense together and turn into molecules. We are made of the same thing light is. Dipole electrons. You see this? 56-mile particle smasher is possible, says CERN report. Yeah, give us enough money and we'll build something like that. Well, and in the same report here, it says in a new study, researchers suggest a simpler, much smaller scale alternative. They gleaned data from inside the nuclei, inside the smallest center of particles without all the hullabaloo. They didn't, the things they smash. Instead, enlisting an atom's own electrons as messengers within a diatomic molecule. I'll explain to you that in a minute. You don't need this. This is extremely wasteful. Now, what they did was they did this by pairing a radium atom with a fluoride atom, forming a molecule, radium monofluoride. Just to break it down and make it simple, they were able to see, using CMOS, the particles bouncing in and out of there. Expelling and bouncing back in, basically, is what they were looking for, and they did see it. The energy, let the researchers precisely monitor energies of electrons within the molecule, revealed a subtle energy shift. Electrons were evidently making brief forays into the radium nucleus and interacting with its contents. So that's nothing more than an isotope. An isotope is nothing more than what they're talking about here, having particles missing or having come back in here. You can have isotopes that are too big, you can have isotopes that are too small. And that's all they're talking about, is the electrons briefly leaving, coming back. That's all an isotope is. All right, I'm going to try to explain this. It's really not that hard to understand. They're taking radium. Now, radium atoms they're ready to fall apart right now. They're radioactive. They're just ready to fall apart. So radium is a good candidate for this. And they embed that particle that's ready to just split apart right now into another molecule, which intensifies the activity of the electrons inside that particle, and it makes them explode them out. Basically, that's the way I'm taking it. I could be wrong, but I don't think so. And this is from co-author so-and-so, a physicist at Johns Hopkins University, who contributed to the study as a graduate student at MIT. Now, I actually went to Johns Hopkins for genomics, but I fully understand what they're doing here. Now, here's in quotations. He says, when you put this radioactive atom inside of a molecule, so you're putting it inside another molecule, and it's in there and it's ready to explode. It's like a bomb inside. All right, when you put it inside of another molecule, the internal electric field, its electrons experience is orders of magnitude larger than compared to the fields we can produce and apply in the lab. Why, I don't know, but it's going to decay, and when it does, something's going to happen inside there. I agree with that. In many ways, the molecule acts like a giant particle collider and gives us a better chance to probe the radium's nucleus. I don't know exactly what they're going to see, to be perfectly honest with you. I'd like to see what their results are to be able to see these things. They're saying they're going to be able to see them. All right, so this is within radio monofluoride. The radioatoms electrons were constrained in a way that boosted their odds of entering the nucleus. Researchers confined and cooled the molecules, then used lasers to measure the energy of electrons inside them. Wow. I got to be honest with you. I think they need to understand dipole electron flood theory, but I would like to see the results of what they came up with. All right, now they say in the big particle colliders, this is outside of the nucleuses. They're smashing particles together. So they know there's many experiments measuring the interactions between the chunks, the nuclei, and electrons outside of the nucleus, and they want to know what happens inside the nucleus. Well, when we went to measure these electron energies very precisely, it didn't quite add up to what we expected. No, because you can't measure this. The energies are not going to be consistent. It's all, they have to understand dipole electron flood theory. It's all about field against fields. Okay, what they're doing seems to be sort of complex as far as I'm concerned. When I showed you what we can achieve just using light and a Venturi and some other little tiny devices, but they're very, very simple, very inexpensive. They're searching for violations of the fundamental symmetries of nature. Just the acceleration of light is right there's a violation. Let's explain that. Let's talk about that. All right, they're looking for these violations of the fundamental symmetries of nature. And yes, if you could accelerate light, that would be a violation. Now they're talking about in a vacuum. If you're going to accelerate it in a medium, that's even better than in a vacuum. And we can accelerate it in the medium of the space that we're in. Now, not only is the speed of light in a vacuum just a speed limit, it's a fundamental constant of the universe. It's a cornerstone of modern physics. It doesn't work. It's wrong. It's totally wrong. It's not correct. It's the fundamental cornerstone of modern physics. Give yourself a few seconds to think about that. Every single thing that they do is built on the fact that light never slows down, regardless of the medium it's in. Like in space, they say it's a vacuum. It's not a vacuum. And they know that anything that light has to come through, it can slow it down. That's fully understood. So if it's coming through something that's not a vacuum, which space is absolutely not a vacuum, it's going to slow it down. And everything is built on a cornerstone. All of these Hubble space telescopes and Webb and all that, how far the distance the galaxies are, no. All of that's based on a consistent speed of light. And Albert just was not right. The cornerstone of modern physics has crumbled. This is also wrong, Einstein. Photons, which are particles of light, are massless. Have no mass. That's incorrect. And always travel at c from the moment they are created. Created from what? They do not accelerate to reach this speed. No, that's not necessary. That's a touchy point. They're created in a snap. Yes, I agree with that. So maybe they don't accelerate to reach that speed, but some of them can accelerate to accelerate beyond the speed of light. So yes, they can accelerate. That's not a problem. I mean, everything in physics is wrong because it's built on the wrong foundation. Lorentz symmetry. A key symmetry is at stake here. Causality. Consistency of C is intrinsically linked to causality. No, it's not. CPT symmetry, charge, particle, time reversal. You can't reverse time as far as I'm concerned. In essence, the very definition of the speed of light as a universal constant is the direct result of the fundamental symmetries. It's the fundamental symmetry, and it's not right. The observed slowing of light in a medium like glass or water is due to interactions with atoms, obviously. not an actual acceleration or deceleration of individual photons. No, it's obviously deceleration. It's hitting them and slowing down. It's unbelievable they don't understand this. And it's because Einstein forced this law, or whoever said, well, that's got to be a law. If it's consistent, it's got to be a law, and we have to follow that law, or whatever we're doing is wrong. Well, the law is wrong, so whatever you're doing following that law is wrong as far as I'm concerned. So here's another one. Speed exceeds that of light. Tachyons have been hypothesized, but their existence would violate everything, so they can't do it. Light as we know it may be a direct result of small violations of relativity. No, that goes back to 2005. And this goes back a long time. I've been showing this stuff for a very long time. Well, since 2013, 2014, and in a kind of an obnoxious way. What's this one, 2015? Is there a relationship between speed and spontaneous? Hold on one second. Okay, I said that faster and faster frequency gives you different colors. This is the red, and it's kind of slow, and you can see this is an upspin because the white is up, and this is a downspin. It's doing this as it reaches the Venturi. Now, the same exact structure particle, green, is here. And you can see it's an upspin or downspin. This is a downspin because it's down. Now, this is getting charged, and it's going to flip. And then it will be an upspin because the white will be at the top. Now, you see how it's straight up and down here, even though it's going in that plane? It doesn't twist and go this way. It stays up this way. It's something to do with the gravity of the Earth to these dipoles. But it's the same particle, only faster. And here I can prove it's faster because this is both of them at the same time through the same Venturi. The red is much weaker and slower, and it gets pushed out of the way as the green continues past and re-impacts way out here. And that's why this barrel rolls. You see them rolling like this way? That never happens consistently. They will roll, but you never see that happen unless you put it through the same Venturi at the same time. And so again, this is Don Lincoln's. It's the exact same thing. He says this does exactly what I claim, and this also does exactly what I claim. This is 2013. And, I've been complaining about him, but that's just a fact. I sent him all this stuff not long after that. And I said that this was dark energy. Light is dark energy while traveling from the sun to the earth. Because it's coming through whatever's coming out of that sun, when it hits us, it's something. It's not nothing. And it's dark energy in the meantime because it's not being excited. You have to excite something to make it glow. They see them glowing because they smash the hell out of them. We see them glowing because we put them through the Venturi. Otherwise, you wouldn't see it. It'd be just like nothing. You have to excite something to make it glow. And here's where it's coming in, and the particle's getting hotter and hotter and hotter, and boom. And that is glow, my friends. That's some serious glow. And these are dark particles. These are the dark particles. And that is dark matter, the muons. They back off of here, and the white squirts through because of the design. And green, I showed you, green is faster and the same particle though. And also, Don says that empty space isn't empty. Empty space isn't empty. It's obviously not empty. And he shows us exactly what I claim. It's like the head of a root beer. Just little tiny particles out there all over the place. And every now and then they bounce into each other, but not hard. They stay sort of apart, keep their own areas, and the light comes through them, yes. Excites them. You see a glow in the universe, absolutely. And that's exactly what he's talking about. And this again, 13, 12 years ago. And again, we went head-to-head on this. I mean, head-to-head, about as head-to-head as you can get. And it's just, here's his particles, here's my particles. And I'm not going to go any deeper with that right now. It's just not, it wasn't good. In my opinion, it wasn't the way to handle it. And now they are using the same technology we use, the CMOS, to see these. And they're bragging about, oh, now we figured out how to use CMOS. I showed them how to use CMOS 10 years ago, at least. We were doing this since 2012. And when I saw Don's stuff, I got a hold of him. I said, hey, we got the same stuff. And again, it didn't work out, and it's chafed me ever since. And we can see all of them. You can see the blue coming in really hot, slowing down. It's no problem to see them slowing down. And this is to speed them up. And when you can speed them up from this to that, that's not allowed. That is a violation of the symmetry. And that is what they're talking about. Now we can see violations of symmetry. I've just shown them for years. Years and years. So I think it's time to talk to me. Now this is coming through the air. This is going through glass. Blue is just too much to see really in the air. It's just too fast. You see how fast that is? Now it's slowing down, slowing down, slowing down, slowing down as it goes through the glass. But you see how it's making that bubble in the glass? Isn't that cool? And all of these little tiny, 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 tiny dots, they have to be some atomic, really atomic areas, or maybe even dipoles. I mean, there's a lot of them. I don't know. This is stuff there's a lot to look at here. There's a lot to understand. But just smashing big things together and getting a whole bunch of debris, that is not getting us anywhere, and not in a single place. And I think we might be able to use this white energy right here and be able to harvest it, because that's all you do when you create electricity, is make the black stay away from the white. You take the white and you put it down in your battery or run your car with it, and it has no weight whatsoever to speak of. 1,000 pounds of battery. You charge it all the way full charge, you can drive 500 miles in a car on that, let's say. And when it's fully charged and when it's totally empty, the only difference in weight is it's 45 thousandths of a gram. There's no difference whatsoever. That's like two little pieces of salt. That's how much of a difference in of weight there is. And you go another 500 miles, you do the same weight, same weight, same weight. Never changes. The white has no weight whatsoever. It's time we get this done and get this out and be able to look at science from a critical eye instead of being forced to say what we were told to say, and then having people just ignore the facts and the truth. Okay, my friends, watch this. This is Professor Shankar.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now I'm the only one who doesn't understand quantum mechanics. In about 7 days all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So,
now he's a nice guy, but he's being honest. This is honest. If he tells the kids, you're going to have to say what I tell you to say, and that's it. Spread your ignorance, and that's the best we can do. Nobody understands it. Well, I try to engage with them. Same thing with that. Nobody wants to engage. But he was at least being honest. I'll give him that much. And they realize that the new physics, it challenges the Big Bang, the story we thought we knew. No, the story we thought we knew is not even close to the real story. And I have evidence to talk about that will explain. See, this isn't long ago. They know they don't get it. They don't understand quantum physics. They admit it. Nobody gets it. And they won't respond to people that do get it. And I do get it. And this is it right here. It's all about the electron muon dipole electron. The two of them together make the dipole electron, which they call a gluon. They know about some of this stuff, but they don't understand how it fits together to make the dipole electron flood theory, which is where all the dark matter goes to the center and all the fluffy stuff goes to the outside. And the closer you get to the core, the brighter the energy level will be, because it's hard to rip it away right at the core. The red you can rip away, and it's not as fast as the green, and the green is not as fast as the blue, and the blue is as fast as you get. And when it's really hugged up to that black, you can make it, you really got to pull it away. And that's when you get your high energy levels up in this area here, in the blues. All right, this is the area where you're just pulling the particles away. Below that, you're sort of shaking them and doing microwaves and radiation. Here, you're spitting out particles in the visible spectrum and these different colors. And the reds are on the outside edge. The greens are a little closer, and the blues are right on the core. Once you get past the blue, you hit what's called an ultraviolet catastrophe. That's up here. And at ultraviolet, at a certain level of ultraviolet, there's no more these left, because you ripped them all away from the black. So now all you have is black. And then if you keep accelerating that, you go through the X-rays and gamma rays, those things will kill you, because this is actual matter. All right, so this is how it works. And the more shaky you get, more frequency is the more energy. It's just hitting a ton of times, or hitting them every now and then. Every now and then is red. That's green. That's blue. And then if at a certain point there's nothing left to bang, and all you got is black left. Now, when they say science and religion and believing in God and all that stuff doesn't mix, no, totally wrong. Jesus actually said, if they say to you, where have you come from? Say to them, we have come from the light, the dipoles, from the place where the light came into being by itself. It established itself and appeared in their image. So the light appeared apparently as something like us. If they say to you, is it you? Say, we are its children. We are the chosen of the living Father. There is billions and trillions of particles falling everywhere right now, and they're not chosen. We somehow became chosen by the living Father. If they ask you, what is the evidence of your Father in you? Say to them, it is motion and rest. All right? Here's Caesar. This is my goose, Caesar Augustus. And he's at rest. He's just laying around doing nothing. But he could fly. He could swim. He could do all kind of crazy things, which is motion. And that's what we are. All our particles are capable of anything. So it can be any kind of motion or just laying around doing nothing. All right, and there's a lot. He said, well, I've been showing, well, I'm not going to get into the rest of the stuff, but he says, search. And this is, when I reference religion and Jesus and gods, which were the mythology, mythology to me is not mythology. It is recorded history. Now, Jesus, this is supposedly the secret sayings of the living Jesus while he was walking around in his flesh. And Judas Thomas, doubting Thomas, recorded all these things. This is the most important one right here. Jesus said, those who seek, and you've got to seek or you're done anyway. So if you don't seek, forget about it. You're off the table. He says, those who seek should not stop seeking until they find. If you're not sure, you got to keep searching. When they find, they will be disturbed. And yes, things are disturbing when you really search. When they are disturbed, they will marvel. Yes, because things are marvelous and will reign over all. And after they have reigned, they will rest. Now remember this is not just one person, or the things that he talks about covers a broad variety of people. When they find, they will be disturbed. That's all of us. You have to look. And also 56 was very interesting. Because there's some people who cannot see what's right in front of their faces. Jesus said, whoever has come to know the world has discovered a carcass. And whoever has discovered a carcass of that person, the world is not worthy. That's not like one person. It's saying whoever. That's anybody. Whoever has come to know the world. Meaning, to me, is either the earth itself or the world as the population of the world. They're both, to me, carcasses. They're dead and not doing what they should have been. The earth is just covered with carcasses. Whoever has discovered a carcass of that person, the world is not worthy. And number 80 says something very similar. It's about bodies. You have to understand anatomy. Jesus says you got to understand anatomy. Jesus said, whoever has come to know the world has discovered the body. Well, you have to know anatomy to discover the body. Whoever has discovered the body of that one, the world is not worthy. Whoever. So there's out of anybody. So if you agree or not, you don't have to agree with anything I say. When I say agree, if you have come to the same conclusions, agreeing just means you say, yeah, I'm going to say what you told me to say. That is not ever what I want. I never, ever want you to be just in agreement to agree. I want you to understand what you see and come to a conclusion, and I would say that in most cases it will agree with my conclusion. So that's how I'm going to leave that one. All right, images, Jesus said images are visible to people. All right, but the light within them is hidden in the image of the Father's light. He will be disclosed, but his image is hidden by his light. Everything's about light. I showed you, number 50 says we are children of the light. We are light. And we are made out of those two particles which make up everything. The black and the white is light. It's their photons, which is the light. Everything is made out of light. So if you don't come to that conclusion, I would like to understand how you can not conclude that. Everything can be split into a million billion pieces and go into these pieces. Yes, nuclear devastation can do that, absolutely. And that's been shown by exploding nuclear bombs. And you end up, this is nothing more than a nuclear bomb hitting head on. You got nothing but pieces. I think I will leave it at that for now, my friends, but it's time to wake up to the reality that we have in front of our faces. And, let's try to understand. Instead of just saying nobody understands it, so just say what I say. No, that does not work. All right, I love you all. Thank you. Bye.